Now I'd like to introduce a talk that will be tag-teamed by two folks from Conviva. First will be Davis Shepard. Did I get your name right this time? Yes. All right. And he works for Conviva, which is a video analytics company, and they have been some of the most strong advocates of Spark in the community, and much like a few of the other applications folks that we've heard from who have given talks and helped us to grow and get more adoption by being early adopters, he'll give us another status update with the most relevant recent developments on the status of Spark and how they're using it for kind of the best of all worlds, or one platform to rule them all, is kind of how we think of it. So thanks, Davis.
Yeah. Sorry, where am I?
Yeah.
All right, everyone. So talk's going to be sort of two parts. I'm going to talk about sort of the application that we currently have running in production, and this is sort of what we feel is sort of a novel and interesting use of Spark, not the traditional sort of word count or roll-up type applications that you see. This is something that's pretty interesting and a lot of fun to work on, and then she will talk about sort of the future that we're going to be working on with Spark. So just high-level summary, I'll sort of talk about our value proposition. I'll talk about the problem, at least in the first half of the talk, about what we needed to solve and how Spark was essential to that solution. And then she will talk about sort of what Spark is going to enable us to do in the future. So I'll begin with just a compelling data argument for why we do what we do. And that is that quality has a very big impact on user engagement in online video. This is from a viewer experience report we published last year, and as you can see, there's a huge drop-off in terms of total average engagement for a user if they spend just a little bit more time buffering relative to the total time they spend playing. So hopefully this is just a little motivating fact to understand why it's important to sort of deliver quality video, whether it's online or in a traditional method. So that brings me to what we do. So we built an internet-scale control platform to optimize end-user online video experience in real time, and that's sort of what I'm going to talk about. In addition to that, we provide historical and real-time metrics for online video providers and distributors, and we also enable sort of multi-CDN infrastructures with fine-grained traffic shaping controls, so customers can negotiate various pricing with various CDNs and decide how to route traffic when. And that gives us a pretty unique insight into the online video market. So we see about 4 billion streams per month, mostly from premium content holders like HBO, ESPN, BSkyB in UK, CNTV. But we also see user-generated video sites, such as Vimeo and Ustream. And we get to see data from live events, VOD, long-form and short-form, all sorts of various streaming protocols, and traffic from all major CDNs, including Verizon's and AT&T's, in addition to the Akamai's and Level 3's. And from all this data, we've surmised a pretty fundamental truth, and that's that video delivery over the internet is hard. It's a hard problem. There's a big disconnect between viewers and publishers. A viewer has insight into the screen they're looking at, and possibly into their sort of last mile internet connection. And if they have a buffering problem, they have no idea why. They might call a provider who only really sees this upstream pipeline that gets shipped over a CDN, and they have no real feedback into how that's actually performing. And so these metrics that we provide helps to close that loop. But that's only part of the picture, right? We provide metrics, but there's still a human sitting there to sort of go and fix these problems. So they can't just go and configure a load balancer to fix these problems, because CDN variability makes it nearly impossible to deliver high quality video everywhere with just a single CDN. And even if you're So, I mean, just to compel this argument, this is data we published in SIGCOM again last year from 3 major CDNs across various cities, and none of them perform best in all areas. In addition to that, there's temporal variation. So configuring a static policy on a CDN load balancer isn't going to fix your problem. So we need to close this loop completely, and that is we need to take this data and turn it into automated, actionable information. So brings me to the core of idea. So where there's heterogeneity in these CDNs, there is certainly room for optimization. For each viewer, we want to decide what CDN to stream from, in a completely automated fashion, no human intervention. but it's difficult to model the internet entirely, and things can rapidly change over time. So we want to make these decisions based on the real-time data that we're already collecting. To give a bit more intuition for that, you could imagine that we have sort of these various heat maps for CDN performance. And we want to compute buffering ratio in these various areas, say top 5 cities. So each one of these cells sort of represents, average buffering ratio of users that play in this CDN in this particular city. Here in Seattle, both CDNs perform relatively well. That's not necessarily the case in San Francisco, for example. And then with that information, we can basically decide to send a client to the best CDN in their particular region. So again, in San Francisco, we see that CDN2 outperforms CDN1, so we'll make the decision when a client comes to join, send that client to CDN2, as opposed to sending them to CDN1. And hopefully, this results in sort of an optimal sort of heat map we should get as a result, which is sort of the cherry-picked best performance of all these CDNs in all areas. Now, again, you might imagine that a static load balancer might solve that problem, but again, because we see these changes in performance, we have to build an online algorithm to adapt to changes in these CDNs such that we are constantly and continuously getting the best performance possible. So, in summary, we need to build a coordinated central system implementing this optimization algorithm that dynamically selects a CDN for each client based on the individual client and when they come to request it, aggregate statistics. Obviously, we need to share state between these clients to make estimations about how new clients will perform. And again, we need to merge this with content owner policies. We can't just go willy-nilly and send traffic wherever we think it will perform best because there are serious pricing ramifications and cost ramifications to sending traffic around. So this is a serious concern. And all of this needs to be based on real-time data. We can't be slow to react to these problems. We need to preempt these sort of performance issues as quickly as possible so that we can say after the fact, hey, here's a problem, we got around it, as opposed to, oh, look, there's a problem, we need to fix it. So at the core of this, we need to be able to process data in a very, with very low latency, which brings us to the question of which processing framework to use. We considered Twitter Storm, but at least back when this project started, the fault tolerance model sort of affects data accuracy. So if there's a particular issue with messages coming in late, we might make a decision that's potentially disastrous in terms of how we route traffic. So that's potentially a nasty failure model for us. In addition, the non-deterministic streaming model makes it sort of difficult to implement machine learning algorithms, and particularly to debug them. We considered rolling our own, which we'd done before for our just basic live metrics processing stack. But from that, we'd learned that it's a bit too complex, especially if we want to get this off the ground quickly. And frankly, there's no need to reinvent the wheel. These things are being done, and we believe there's a system out there that could do it. And of course, Spark was there for us. And had the benefits of easily integrating with our existing Hadoop architecture. And additionally, the sort of flexible, simple data model is really nice to use and think about when implementing these complex machine learning algorithms. And in general, map is sort of nicer to work with than update. So with that, we built a system. We have a Spark cluster that's essentially computing this heat map of performance of CDNs in real time. It's essentially shipped out to the storage layer, which is essentially the driver node, and broadcasting this information over Kafka to decision makers that are in data centers all over the world, which then relay this information to clients, in millisecond response times, because obviously they can't be waiting there for us to think about how to route traffic if we're delaying their video playback. So we've had this running in production for about 9 months at this point, and just to sort of give a compelling argument, we had, we do this for a subset of our customers right now, and we've been, slowly rolling out more and more customers, and we were able to take one of our sort of mid-performing customers and elevate them into our top performers just by using this sort of optimization algorithm. So it's really exciting to know that, we're able to leverage this real-time data processing to make, actionable and appreciable improvements in online video streaming. Now, it wasn't all smooth sailing. There was a lot of problems. We came into Spark around 0.5, and there was quite a few problems that we faced. Silent crashes being one of them, which was, again, and a lot of these have been amended with the more recent versions. Our recent upgrade to 0.8 has been a real breath of fresh air. The problems with debugging now are sort of a thing of the past because of these instrumenting tools that have now been built. And again, these things that we suffered with the early versions have been sort of sorted out, which is really, really nice. But again, configuring Spark is sort of a key problem that you need to get around. But I think the most important thing that we've learned, at least with our experience with Spark, is that a fundamental understanding of the underlying data model is essential to writing effective Spark programs. And if you guys get a chance, I know a lot of Patrick's talk in the earlier session was really, really helpful in sort of talking about these things. And if you didn't get a chance, you should at least look at the slides. Because you know, as you're building these things, it's really easy to get lulled into the very simple and expressive interface and write potentially disastrous programs. So now, this was all in place. And as I mentioned earlier, there's these pricing concerns with CDNs. So in addition to computing this heat map, which was great, and we showed this initial result, we had to enforce constraints on top of this optimization. And just to give you some intuition, you can imagine, so I have this heat map now, but I want to make sure that only half my traffic goes to either CDN. So I see in this particular region, I want to send a client to CDN2 instead of CDN1, but I'm now sort of violating these constraints because I'm sending more traffic to CDN2. So in this other region, I send a client back to CDN1 as opposed to CDN2. I'm back sort of within constraints, and this net change has now improved sort of global utility. And you can imagine repeating this process until sort of an optimal solution is reached, until any movement doesn't really improve utility. You've reached sort of this convex maximum. Now, the problem with this process is that the solution is found only after clients have already joined. So therefore, we need to parameterize a solution to this problem to clients seen for online use. We can't wait for them all to join, aggregate them over time, and then compute a result, and they sit there for 5 minutes waiting to join. But as it turns out, you can actually compute an LP on offline data and parameterize the solution for online use. And Spark supported it, which is, sort of a tribute to the fact that it has such a flexible data model that we can do these sort of very exotic or elaborate things in this distributed way. And just to give you an idea, 20 LPs, each with 4,000 decision variables and 350 constraints, can all be computed in parallel in about 5 seconds, right? And this is sort of horizontally scalable. As we have more LPs that we need to compute for various policies, we can continue to scale with it. Now, another problem with all these algorithms is that there's a lot of tuning involved. We can't just select a CDN based solely on one metric. So we need to sort of be able to explore utility functions that best predict engagement, right? If we're just optimizing for buffering ratio, but that doesn't really affect how users are engaging, or it's not enough to affect how users are engaging, we might need to look at more particular startup metrics. In addition, confidence in decisions will depend on how much data we've collected. So we need to be able to tune time windows and select different attributes for separation and decide how much correlation there is in temporal data. Which means that because the space is so large, we need to be able to validate these algorithm changes quickly. So essentially what we needed to do was be able to simulate these tuning parameters offline and quickly. And again, we're able to do this all on top of Spark, reusing the vast majority of the code we already have, right? It was a simple layer to simply pull HDFS production traces from data we had already made decisions about, at least for a randomized initial decision, so we can actually do improvement analysis. We generate a decision table just as we would in production with an artificial delay. We produce a simulated decision set, again in parallel on Spark. We essentially simulate the query layer on top of Spark. And then we can evaluate these decisions against actual traces and predict uplift. So, this is yet another sort of a case where, again, we have this extra requirement, and it was very easy to sort of, build these extra features on the existing architecture. So Spark in general provided us a very sort of rapid development environment, aided both by its excellent programming interface and, again, highly active community. I can't stress that enough. It's really excellent. It's a very expressive sort of language, so we were able to develop this complex online ML decision algorithm in about 1,000 lines of code, at least in its current iteration. And as a result, it's very easy to prototype these various algorithms. And it makes scalability a far more manageable problem, right? We can go about thinking about the interesting thing about how to do solve this regression problem, and not about how are we going to process all this data quick enough. And so after these initial teething problems, which are now really a thing of the past, we've been running Spark in a production environment in a 24/7 sort of streaming mode reliably for 7 months now. Or, yeah, 7 months. So we're very, very happy with our experience so far. So to introduce Xi's talk, eventually we're going to be leveraging Spark streaming in a more broad sense for all of our metrics processing stack, which will allow us to unify multiple things and eventually allow us to build a platform to build various processing apps, e.g. anomaly detection, customer tailored reporting, all in a sort of unified system. I'll skip over those since those are at the end. So.
Hello. So my name is Xi, and also I'm an engineer from Conviva. So as the first part of this talk, you already heard from Davis that our sort of pilot Spark application is a success, so that we ask ourselves what's next steps. And we actually have we'll come up with a roadmap with a lot of Spark application in it. Davis will just show you as sort of a list. So in the second part of this talk, I'm going to just talk a little bit about one specific project, which is the unification of our real-time, near real-time, and offline stacks using Spark and a streaming Spark. So let's first look at our current sort of dual stack architecture. So at this point, you probably already know that Conviva is in the video control plane, that we collect video events from millions of video players, agents at any point in time. And when the data actually come to our backend, they go through two different passes. So first of all, we log all these events onto HDFS, and periodically we have, every 5 minutes, we have trigger a Hadoop jobs to process all this data. And we also roll up for like hourly, daily, and monthly. And the data produced in this stack is persistent, and we store them back to a persistent storage. At the same time, we also have a real-time stack. All the data go to that stack as well. So the granularity and the delay for that stack is about 1 to 2 seconds, and which apparently that we cannot do this with Hadoop. So we actually come up with our own in-house streaming solution to deal with this problem. And the one thing I want to note that the metrics produced in this stack is ephemeral, which eventually will be corrected by our data produced by the offline stack. So, on the surface, the dual stack architecture looks fine. As my understanding is that actually a lot of companies have similar architecture. However, we have been running the sort of dual stack architecture for actually more than 4 years now. And one thing we learned from this experience is that the devil is in the details. To be more specific, the biggest thing we learned is that the streaming model is extremely complicated. So when we started to writing applications, it's a simple application, everything was just fine. However, over time, our application gets more and more complicated, and what we found out that the streaming model is much harder to reason about than the batch model. We have, what's ended up happening is that we have many, many more bugs in the streaming system than in the batch sort of processing offline system. So what makes things even worse is that the streaming model is not deterministic, right? You have the same input, you may not all get the same sort of output all the time. This actually makes our debugging is a much harder process to do. This is one of our biggest headache. Sort of another issue with this sort of architecture is that we have to maintain 2 separate code bases, and that's very costly to us. For every new feature, for every change we have to make to this, we have to write code twice. And sometimes we have implementations that just out of sync between the 2 sort of code bases that cause discrepancy between the two stacks. So to solve this problem, we actually trying to use a streaming Spark to solve this problem. So the streaming Spark is actually a streaming system, but under the hood, it actually uses a batch model. So this is not a talk about the details of the streaming Spark system, but I'll give you a very short summary that the Spark and the streaming Spark provide unified batch model, unified API, and unified fault tolerance model. So what this really means to the application is that you just write application once, And then you can run this in both the real-time and offline mode. It's just with the different batch sizes, right? So real-time is just a couple seconds batches. Offline is basically 1 minute, 5 minute, or these the batch sizes. So another nice feature of this streaming Spark system that actually can provide exactly one semantics, which is actually a requirement for our application. So, so we actually finished our first phase of this sort of project. We have migrated our application over to Spark and Streaming Spark. It is not in production yet, but we already seen significant sort of reduction in terms of lines of code. So I also want to note that not all the reduction comes from this unification. Some comes from the fact that we move from Java to Scala. Some come from the fact that we don't have to maintain our own sort of custom in-house real-time stack anymore. But the bottom line is we are very happy about the results, this state. So that's about the good things about the Streaming Spark. And every system, every design choice has its trade-off. And the Streaming Spark is no exception. And in this particular case, I think it's performance. So first of all, I have to say that the Streaming Spark guys actually did a very good job optimizing for very small batches. The truth is that we didn't even think that such approach is even possible before, but the Streaming Spark guys prove us wrong. But however, our very initial numbers, what we see is that we see about the 2x performance degradation. Or put it another way, we need about twice more resource to handle the same amount of load. But again, this is a very sort of initial numbers. We have not fully optimized our application yet. So that's sort of like the fundamental trade-off. There are also other things that if you're going to use the Streaming Spark tomorrow in production, it may not be ready because it still needs some work. Things like it needs some work on the API side. It probably need a better fault tolerance model in terms of its input, especially if an input is from Kafka that potentially allow you to do that. And there's also other things like if you have a high load, you might want to increase your batch size to handle that scenario. But my belief is that the Streaming Spark guys will actually solve these problems in the following releases. So there's actually also another alternative solution from Twitter, which is the combination of Twitter Storm, Trident, and Hummingbird. So the Storm, as you probably already know, that's a very popular streaming framework. As a Trident actually provides a batch processing and exactly one semantics on top of Storm. Hummingbird actually provides a write code once sort of capability that you just write code once, and you can run this application in both Hadoop and Storm. So personally, I have not evaluated this sort of alternative solution, but very high-level summary is that Streaming Spark is a very cleaner solution that's from scratch is sort of designed to have a batch processing model in mind, while the Twitter solution is more like one tool on top of another to achieve the similar goals. However, on the other hand, my sense is probably the Twitter systems are probably better, more battle tested at this point. So in conclusion, so in the last couple of years of running this dual stack architecture, what we learned is that simplicity is very important. And that's why we like the simple batch model. And the Streaming Spark and the Spark is actually the tool to enable us to unify our real-time, near real-time, and offline stack under this one single simple batch model. And the trade-off is that we need extra resource to do this. But to us, we believe that it can be justified by the simplicity of the model, the lower code maintenance cost, and potentially faster development iterations. So we have a booth over there, and if you're interested, you can come to talk to us. I don't know if we have questions, time to take questions.
One question.
Hi, quick question. So you mentioned that there is a performance penalty when you use Spark streaming. So do you know which aspects of Spark streaming is the one that is contributing to the performance degradation or the times 2 factor?
Yes, so if we think about it, it's actually pretty close to the argument of immutability and mutability sort of case. And it's basically, you have sort of input, right? You get some output, and so it's, how to say that? How to phrase that? So the question is in terms of what's contributing to the degradation and in terms of performance, right? Okay. So because so I'm not sure if you're familiar with the sort of immutability versus immutability argument here. Basically, in some sense, it's like a data transformation, right? Versus you're updating states all the time. That's one of the things to us because we run a state machine in our application. So in a batch, you're basically one states and sort of the other one, versus sort of constantly you could just update the states. That's one of the, I think, one of the major reason for us, at least for our application.
I mean, in general, right, there's lots of sort of optimizations within our current live stack that are sort of tailored specifically to our use case, right? And obviously something as generic as Spark Streaming to handle all these types of use cases isn't necessarily going to benefit from the tribal knowledge about how our data actually works. So, I mean, that in general could explain a 2x degradation. And frankly, 2x is damn good considering how much optimization is in our current stack. So, I mean, we're still pretty pleased with this. It's not really a deterrent in our case.
All right, let's give them another round of applause.